Okay, that's enough. All right. Hi, everybody. I'm David. I'm a solution architect at Couchbase, and before that, I was a big data consultant, and I did stuff with big data. And today, I want to talk to you a little bit about databases, specifically NoSQL databases versus SQL databases, and what those things are, what we can do with them, why they're good, why they're bad, and whether you should even bother learning about them to begin with. So, before I dive into all that, I want to start with a little story. And this story is from last year. I go to customers a lot in my job, and I meet a lot of customers and I help them get started with Couchbase, which is where I work. And this customer is a very big customer in the advertising business, and they had an existing system based on MySQL and .NET with a web interface that did some very simple stuff, right? It had a bunch of business entities. It let users come in and edit those entities, and the different entities had different relationships, parent, child, and you could show lists of entities and edit them. So I think everyone who's ever worked on a regular business system can imagine exactly the kind of thing it was. And most of you have probably written two or three of those yourselves in your careers. So it was a nice enough system, and at some point they decided to upgrade the whole thing. They were going to rewrite it and make it modern and, sexy and open source and all that stuff. So they switched from .NET to Java, and they said, all right, well, since we're modernizing, we're going to go from MySQL to NoSQL. And we're going to do that. And they started shopping around, and they called Couchbase and said, come in, let's talk about Couchbase. We really like it. We want to use it. So I went over there, and it wasn't very hard sell, obviously. They were already set on using Couchbase. They were almost a month into development. And I sat down with them and started learning about the system because it's my job to help them do it, right? And the more I learned about it, the more worried I became because it was a very simple system. They had maybe 1 million entities in total in their database. And obviously, within the first half hour, my first question to them was, why would you even use Couchbase? But of course, they didn't say that because I like my job. So we kept meeting, right? And we kept going and going. And eventually, we dug to the root of the problem of why they started looking at NoSQL in the first place. And it was for two reasons. First, they're engineers, they're all geeks, they like cool technologies, and they want to have a very nice item on their CV which says, I used Couchbase. Which is fine and understandable, and it's a perfectly good reason. And the other reason is they have a very complicated new permissions system which they needed to implement, where different objects had different permissions. They had to inherit permissions from one to the other. So if you changed the permission on one object, it had to trickle down to a bunch of those. And they tried implementing it on MySQL and discovered that every change would lead to about 10,000 different changes down the line from that object. And it wouldn't really work very well on MySQL. So they said, all right, well, forget it. We're not using MySQL anymore. We're going open source and NoSQL-ish. And they downloaded a bunch of NoSQL databases. And each one generally comes with a tool that lets you do some kind of benchmark, some kind of insert test or something. They ran all the tools. Couchbase came ahead by a little bit. They said, all right, that's the choice. We're going with that. And at this point, I said, all right, well, did you try doing the permission thing with Couchbase? And said, yeah, sure, it's great. We do the 10,000 inserts, and it takes 1 second. I said, all right, but it's 10,000 inserts for one change. Why would you do that? What happens when you have 20 users or 50 users, each one changing permissions? That's right, we'll scale the cluster. We'll add more machines. It's great. It's scalable. You can distribute it to more machines. And at that point, I almost said, well, all right, why wouldn't you look at other databases like Neo4j, which does graphs, and it would actually work very well with your permission systems, because you could separate that, keep everything else in MySQL, use just Neo4j to do the graph of permissions for all the objects, and do that. But obviously, I didn't say that either, because again, I like my job. And it was a very easy sell. Our sales guy came in, sold them a bunch of licenses for Couchbase. We were very happy, obviously, but unfortunately, I ended up stuck helping them implement this monstrosity, and I've been doing that on and off for a while now. And my point is this. Well, several points actually. First of all, that was a very silly way to evaluate databases, and you shouldn't do that. And we'll talk about better ways in a bit. Second, engineers are human too. Everybody likes to play with cool technology. Everybody likes to have a lot of different buzzwords on their CV, and that's good and that's fine. But sometimes it's not the best way to pick databases either. And the last point is even though there usually isn't one database which can do everything, usually one database can do maybe 80% of everything. And all you need to do is find the one missing piece to do the other 20%. And you don't have to go and find a database which will do everything and then misuse it in the worst way possible, unlike those guys. All right, so again, now we're going to talk about SQL and NoSQL, which, by the way, is a terrible, terrible buzzword. I hate using the word NoSQL. I keep saying it's on and on and on, but I don't like it because it's been horribly abused by marketing departments, and it's completely meaningless. Because talking about SQL databases versus NoSQL databases is like dividing the whole animal kingdom into apes and not apes. All right, which is reasonable because everybody likes monkeys, right? But it's not a useful way to talk about animals. Neither is NoSQL a useful way to talk about data stores. What we're going to be doing is we're going to be defining some much better specific criteria for how you can talk about different types of databases and different types of data stores, what they're good for, what they're not good for, and how you can compare both within each family and outside and between the different families, right? And then we'll see some demos of what you can do with them. So before we start that, quick survey, small poll. How many people actually write code for a living? Just raise your hands. Everybody, that's really awesome. How many people tell other people how to write code? A few people admit it. All right, good. So in your lives, how many of you have used a SQL database, any SQL database? All right, very good. How many people recognize at least 3 of the names or logos on this list? How about 5? Hands are starting to come out. How about 10? Like one guy in the corner goes, yeah, I know all of them. I should have put one on that doesn't exist just to test it. Just thought of it. Oh, well. Well, obviously, everyone's heard of my SQL Server, right? I put that on just to make sure at least one person can say, yes, I've used it. But all right. But clearly, people have heard of them. But OK, how about this now? How many people have actually used one of these in production, not counting SQL Server? How about 3 of those in production? One guy going, oh, 2, sorry. Well done, sir. Well done, sir. OK, how about 5? I'm just waiting for everyone to just put your hands up. All right, no one's actually used 5 of those in production. OK, so this is a bunch of names, and I picked some of the better known data stores, NoSQL data stores out there. If you go to, for example, DB rankings, this is more or less the top 20 minus the SQL ones. And first thing we're going to do is we're going to start categorizing them. And the biggest and simplest category is key value stores, which covers pretty much almost every database because it's just such a broad definition. But it does tell us something useful. Key value stores, exactly as the name implies, are generally just a hash map in a database which lets store data under a specific key and just retrieve it with that same key. Now, there are specific databases which are purely just key value stores, like Memcache and Reddit and Ryak and a few others. And some databases started out as a key value store and evolved into some other stuff with more features. But just as a pure key value store, we can have a lot of very useful functionality in the key value store. Generally, what defines the key value store? Shouldn't switch? Yep. Mostly the fact that the value itself is opaque for the database. The database doesn't need to understand it. It doesn't care what it is. As far as it knows, it's a bunch of 1s and 0s. And that's a wonderful thing because it lets the database do some very important things in performance and scalability. Because since it's just a hash map, it's just a bunch of keys and values, it's very easy both to distribute because you just devise some kind of schema to partition the key space into a bunch of chunks, put each one on a different machine, and there you go, scalability. And also because there's so little functionality the database needs to do for each query, it's very fast and very, very performant. So all those databases which are pure key value stores like Memcache and Redis and so on, they're very good at their specific domain, which is usually either caches. Memcache has cache in the name, or things like storing session data, storing frequently changing data, or serving as a front end for a slower, bigger data store. Some of them actually add extra functionality on top of the basic key value. For example, different data structures on top of the values. So Redis and Ryak, for example, let you keep lists and maps and sets of values. Now, each value in itself is opaque. The database doesn't care what's inside it, but it gives you very useful semantics to store a bunch of objects and retrieve them very quickly and very easily. So things you can do with key values are anything from storing a shopping cart, which is a real example. I know a bunch of companies which have a e-commerce site, and they just use some kind of key value store, often Redis, to store the shopping cart, because it's something that's very transient, but needs very fast access. But if you start thinking about it, a lot of applications which you wouldn't normally think of as just transient data with key values, you can implement it on top of a key value store. Because it's not just a key value, you can generate keys in all kinds of ways. All right, but I think we're pretty much clear on the key value thing, so we'll get back to it, but I want to move on. And within the family of the key value stores, we can define a subset, which are document databases, which is a very logical extension of the key value concept, which is instead of having the value be opaque, let's store it in a format that the database understands, a well-known format. And the choice of the day is obviously JSON. Everyone loves JSON right now, but it's not a new concept. So 15 years ago in the university, I worked with an XML-based document database. So it's not a new concept. Just these days, it gets a lot more airtime, let's say, and a lot more use. And once you actually define a well-known format for your values, you can do a lot of interesting stuff with your key value database, like searching or indexing the content of your data and updating, instead of the whole value, updating specific fields of the data. So for example, obviously the most well-known NoSQL database is MongoDB. If you ask someone, give me an example of a NoSQL database, everyone's going to say MongoDB. To my great disappointment, obviously, I work for Couchbase, but still, facts are facts. And Mongo, for example, the reason it's so popular and the people use it is that it gives you NoSQL semantics, document database semantics, but keeps a lot of the core concepts that are familiar to people who know SQL databases, things like the way indexes work in Mongo, or the way in-place updates work, and just makes a lot of sense. And it's very easy to reason about your data, even though it's formatted as documents, as JSON documents, which can be nested and all kinds of stuff. And when you talk about document databases, the major shift in mindset that you have to do when you start using them, and the things they're actually good for, is storing complicated object graphs. Because those are very easy to express as documents. You can, if you think about any kind of application that has objects, which is pretty much most of them, what's an object? What's an application entity? It's usually either an object or a graph of objects in the application memory, which if you want to store them in a relational databases, chances are you're going to do some kind of ORM, and you're going to split those up into a bunch of tables. And to get it back, you read a bunch of tables, join them together, and assemble your object. Whereas with a document database, you just do the same thing, except you don't normalize the data. You just serialize the data directly from memory into one big document, JSON, XML, what have you, and store that thing in the database. And when you want to bring it back, you just get one single item, deserialize it, and you have your entire graph of entities in memory exactly as it was. It's not always the case. Sometimes it makes sense to normalize it a little bit, but that's general semantics. And within the concept, there are different streams of thought. Some databases let you update specific fields within that giant object graph. For example, Mongo has a specific field update, which on one hand is very efficient because you can send just one item to update. On the other hand, it forces a lot of compromises in the data store and different databases which choose not to allow single field update, which make you overwrite the entire object. For example, like Couchbase, obviously trade off less network performance and are harder to reason about, but they get major performance improvements in data storage because they can actually just write sequentially all the new objects and not have to update specific items on disk in place. But in general, document databases are very good for your applications. If you're working with entities, you want to store complex hierarchical structures. If you want, for example, to store directly from the web, because everything these days in the web works with JSON, right? So instead of converting JSON to objects, then from objects into a table, and then reassembling the whole thing, you can skip half the process and just take the JSON, put it in a database as a document, and the same thing in reverse. So it's very easy and very convenient for a lot of applications which deal with objects as a whole. More so, they're very scalable because, again, they're extending the same key value concept, and there is no connection between different objects, right? One document is entirely different from the other. There is no joins. There is no any kind of interaction between them. So it's very easy to spread them out to as many machines as you want within reason. And it's very easy to scale and very, very fast to retrieve, because still it's just a hash set, essentially. So obviously I don't need to teach anyone what JSON looks like, but generally if you go from a relational database to a document, you would take something that's a table or several tables, and in this case, for example, if we had a user table and an address table, we'd combine those two, and our user object would be just some fields and a sub-object, which is the other table. So it's denormalized from a relational model. And if you're converting a relational app into a document, it's usually a fairly simple way to think about it. If you just ignore the database and just think about your application entities and just map your data that way and completely ignore the way it's stored in your relational database. Now, the next group we have here are row stores, which often very much get confused for column stores, which we'll talk about in a little bit. But this group is partitioned row store databases, which are about as close as you can get to relational databases. They're essentially very large tables. The difference is there's no joins, and the tables are broken up into ranges, and you can now partition them and store them on as many machines as you want. That's the way you scale them out. The table has a row key, or sometimes called a partition key, which is how the database partitions data between different nodes, between different shards. And the data itself is stored in a simple table. So if you've ever worked with any kind of SQL database that has table partitioning, it's the same idea, except since the database doesn't even have joins, there's no issue with various features that kill performance in SQL databases when you partition data. So that's not an issue to begin with. And so partitioned databases, partitioned row stores, are very efficient at storing large bulks of flat data. So if you have a very big nested structure, it wouldn't work very well as a single table or even a set of several tables, because it would be very hard to reassemble back. It would not be a very efficient query. But if you're storing a lot of flat data, I'll give you an example. Best example is always logs or events. Any kind of events which stream in real time, and each event is just an immutable fact. It's not a large nested structure. So storing events or any kind of time series data would be very good for any kind of partitioned row stores, because again, since it's just regular stores, except regular stored tables, except broken up into ranges and stored on different machines. Some row stores, like HBase, which comes with Hadoop, that connects us to the previous talk that was in this room. So Hadoop comes with HBase built in. Usually most distributions do. And HBase is a very interesting row store because it has a nifty feature that every cell isn't just a single value. It stores all the values that were ever in that cell with timestamps, up to a certain limit which you can define. So when you retrieve data by default, it gives you the latest value, but it doesn't have to. You can also do queries on older values of that same cell. So for example, if you want to store, let's say, sensor data for a bunch of sensors, you can model it in two different ways. You can either just, for every sensor tick, just add a new row, or you can just define a bunch of rows for every sensor and then keep updating them with a timestamp value within each cell. And then if you want to get the value for a specific timestamp in the past, you can just do a query on that row with that timestamp. So they let you reason about flat but very large bulks of data in different ways. And generally, the two big ones in this space are obviously HBase and Cassandra. And Cassandra isn't one thing. It's actually two different use cases. Cassandra can either be Apache Cassandra, which is a free open source database, which you can just download and start using, or it can refer to DataStax Enterprise, which is actually a platform which includes Cassandra, the database, and a bunch of other tools. And we'll talk a little bit about that and why it's good, but mostly because it comes not just with Cassandra, but also with Solr, which is a search engine. How many people were in this room for the search engine talk earlier? 2 people. All right, so it wouldn't be useful for me to. So Solr is a search engine which does full text search and indexing. It's very good for analytics. And DataStax comes with that built in, as well as several features of Hadoop, like Pig and MyProduce, which let you run very large bulk queries on top of Cassandra. And I'll actually show a demo of how to do that, sort of. All right. Next group, which is entirely separate from the key valued concept, is column stores. not to be confused with column-based databases, which is just partitioned row databases. Now, column stores are, if you think about the way a regular relational database stores values, is for every row, all the data of that row is stored together on disk. So if you think about our relational table like this, in a SQL database, how would that be on disk? The whole row will be together on one disk, and the next row will be after that on disk, and the next row after that. So if I wanted, for example, to retrieve all the cities from my relational table, how would the disk behave? It will go to wherever the cell is on the disk, read that, skip on to the next row, read the cell from that, skip on to the next row, read the cell from that, which is very inefficient disk-wise. And also it's very hard to compress this data because the row is the data within one row is very different. We have an integer, we have a string, we have a bunch of stuff, so it's very hard to compress. What column stores do is they turn it upside down. So upside down meaning the data for each column is actually stored together on disk, which if you think about it, makes it very easy to query and aggregate the data for one column. So for example, if I store all the cities in one continuous file, and I want to count how many distinct cities there are, or how many users live in each city, all I have to do is just read sequentially from the file and count all of them, and there we go. It's very fast. It's sequential access. Furthermore, because normally columns are data with very low cardinality, so for example, how many ages could there be? If we store age as an integer, how many different values could there be for age? Let's say 120 if we're very optimistic. So if we have 120 different potential values in a column, it's amazingly compressible. You can express this with 5 bits of information, right? Five. Right, so instead of writing a long value, which is 4 bytes, you can write the same thing with 5 bits and compress it by a factor of about 10. So column databases are specifically oriented for things like analytics and bulk aggregated queries. Some of the more common ones would be HP's Vertica, which is a very popular analytical database, which does exactly this. It stores data as columns and does aggregations and complex queries on top of that. And some of the mainstream databases actually have a mode which turns them into column databases. So for example, SQL Server, Microsoft SQL Server, as of I think version 12, has what's called a column index, where you create a column index table, it does exactly that. It stores all the data. Instead of per row, it stores them as columns with compression and all that. And you can query that with aggregations, which are very efficient, over the column index. Last, but certainly not least, my favorite category of databases is the graph databases. And graph databases are off to the side because they're a very different animal. And they're very specific for storing data as graphs, so storing entities and relations between entities in the same data model. And graph databases let us treat and reason about data with graph semantics. So let's give an example. A few years ago, I worked for a company, and we made a product which let you track a lot of entities and find connections between different groups of entities. So for example, you have people have cars and phones, and they call each other. And our product would let you, for example, define a group of people and find another group of people which is connected to them through a sale of the car. So any person in the first category who had a car, who is now owned by a different person, that would be something we look for. And we obviously, that was quite a while ago, so we implemented that with SQL Server and .NET. Everyone's favorite tool. And that was actually a very hard thing to do. We had to, for example, limit the number of jumps you can do from one entity to another to 5, because we found that generating a query which goes and does 5 different queries of whose parent and then join to another table, rather joining the table to itself 5 times, was so unwieldy it just killed the database performance. And these queries took a while. Each ran for several minutes. So that kind of graph, essentially query on SQL Server is just very difficult, very hard to reason about, and very hard to implement and run. Whereas graph databases are specifically designed for exactly this kind of thing. You define your objects and the relationship between them, and you have a specific language for querying your entities based on their relationships. By the way, I earlier today noticed that the talk after mine but Jan's talk about modeling game worlds with Neo4j. It's actually a blog I read a while ago and I really liked, so I just noticed that he's talking after me. Highly recommend everyone stick around and listen to that one. It's going to be really interesting. That was just a small aside. All right, so graph databases would take something like this from a SQL, so relational semantics, where we have a table, and each row says what other row it's connected to. And for example, the first row is the mother of row 11, and the second row is the mother of row 12, and whatever it is, and express it as a set of edges and nodes and vertices on a graph. And then when you want to query it, you would have specific semantics for querying on a graph. So there are several different graph databases, but the first choice for most people is usually Neo4j. And the second after that is Titan, because it has very good bulk performance. And Neo4j has a query language called Cypher. They have the whole matrix thing going, so Neo and Cypher. And the first time someone explained to me how to create Cypher queries, I was just completely amazed. I had an epiphany. And the way you write Cypher queries is you first sketch it out on a whiteboard. You draw circles and lines on a whiteboard. So for example, if we want to find all the items A, which is the mother of all the items B, how would you draw that on a whiteboard? Do a circle with A, arrow B. And that's how you generate Cypher queries. You turn this into ASCII art, and that's a valid Cypher query. And that was just the coolest thing I've ever heard. That was years ago, admittedly, but that was the coolest thing I've ever heard, and that's why I do NoSQL databases today. This thing. So if you like that, stick around for the next talk. I think Jan is going to talk about something similar, so it's very cool. But I just wanted to show you. But in general, why would you use a graph database? And would you use a graph database for just anything, for a general database? I think Jan is going to say, yes, I would use it for everything. But the answer is probably not. But if you think about the first story I told when I started the talk is, if you want to implement something, some kind of system, which just needs a regular database, but you have this one thing which doesn't suit your database semantics. You have this, for example, security model, which is very complex with many levels of hierarchy and inheritance. You can definitely refactor that out and put it in a different database, and that's a perfectly good choice. All you would have to do is create some kind of orchestration between your main data system and your graph-based security data system, which wouldn't be that hard. You would do it on a software level. There's no need to connect the two databases together. And that would solve most of the problem that's preventing you from using a database that's actually very useful and very easy to work with, because everybody knows SQL, right? I don't think a single person didn't raise their hand when I asked how many people work with SQL, right? So that brings me to my to the topic of actually choosing between SQL and NoSQL. As much as I dislike the term NoSQL, which is silly, but again, if you were going to choose between the different families of databases, we could say that all the SQL databases, all the relational databases, are a family of their own. And if we put that on that circle on the graph I had earlier, on the slide I had earlier, it would just be a circle off to the side. And most of the SQL databases these days borrow a lot of the features from your general NoSQL databases. So for example, if we talk about NoSQL databases, what are defining features for them? Usually most of them are scalable, so they're usually distributed. And usually they all boast either a very high performance or very high availability of one of those. If you go and read some marketing from those, and everyone has excellent marketing, so you'll probably read words like scalable, high availability, blah, blah, all that stuff. And all the SQL databases today have all those things. So MySQL has MySQL clustering, which does do sharding and clustering and high availability. Oracle has RAC, which it had, I think, for 10 years now, so it's not new. It's not anything that NoSQL database has invented. And PostgreSQL, for example, have JSON as a data type as of version 9.4, I think. I'm not sure. So they have JSON as a valid document data type, and you can do JSON queries in PostgreSQL with regular SQL semantics, right? So it's not actually useful to talk about, as I said, SQL versus NoSQL, and SQL databases can do most of the things you would want in a NoSQL database. So if you're going to start, for example, looking for a database for a new system that you're developing, first of all, the first thing you need to do is figure out if it will work actually on a regular SQL database, because there are some very good reasons to use a SQL database that have nothing to do with the database itself. It has to do with the fact that SQL has been around for like 40 years, I think. Everybody knows SQL. It's very easy to find SQL developers. They have a huge library of tools. It's very easy to reason about. All the frameworks and everybody works with SQL, so it's just a very good environment to be in. And if you can stick with that environment and maybe just cut out small slices of functionality which don't work very well with SQL and put it somewhere else, that's a very good choice. Now, when does the SQL thing start breaking down? It usually starts breaking down in one of two cases. Either your data model is just so different that you cannot map it to a relational database because, for example, it works just really well as a graph. Or you're talking about volumes of data, which maybe not big data, but enough data that SQL cannot actually handle it. So we're talking maybe 10 million rows. And I've seen Oracle installations which had a petabyte of data in them. But the thing is, the more data you load into a SQL database, the more features you have to give up. So for example, if you're using a SQL database normally and you have 10 million rows, you can do queries, joins, everything you want. Now you move that up to 100 million rows. Suddenly you have to stop using so many indexes because indexes become very expensive. So all right, you give up some indexes, that's fine. You still use your SQL database, no problem. But then you move it up to, let's say, 1 billion rows, still within the realm of possibility for SQL databases. But now you really cannot do joins anymore. There's really no practical way to do joins between 1 billion rows and another 1 billion rows. And now you start partitioning them, right? So you start splitting the data file into more data files, or maybe you shard them into a cluster, and then you give up more and more functionality, which essentially cuts down your SQL database into any one of the NoSQL databases anyway, so you might as well just use that because it will work better. But until you reach that limit, until you pass the milestone of, let's say, 10 million lines or 100 million lines, there's no good reason to look for something else, unless you really want a very nice item in your CV, in which case, knock yourself out. It's a good reason to use it. That's why I started using NoSQL databases. I wanted to have a better CV. But besides that, right? Okay, so let's say, yes, we looked into SQL databases for our new notional imaginary system, and we didn't like it. It doesn't work for us. Now what? Well, now before we jump into benchmarking and downloading and trying stuff and starting writing code, we need to think first of all whether our data model actually fits the database we're looking at. Or more to the point, we need to think about how we want to store the data, and then look at this very large slide with all the different databases on them, and figure out which ones aren't going to work for us in the first place. So if we're looking at an application which is just your regular business application, chances are the kind of data semantics we want to use will work either with document databases or some sort of row store, depending on how many objects you want to store. If you're looking at storing, let's say, a very complex game economy, then you will probably look at graph databases, because you have a lot of interconnected entities. And if you're looking to store just a bunch of logs, or just any kind of sensor or flat data, you're going to be looking at something that can just store a lot of data. So either you're just going to not use the database at all, which is perfectly valid. You can just write all of that stuff to Hadoop and do MapReduces on them for all day long. Or you can pick a data store which is just very good at storing large bulks of data, namely any kind of partitioned row store like Cassandra or HBase, and just dump all your data in there. And then either use the relatively few built-in tools for working with this data in a database, or use any number of big data tools to work with the data externally. So just pull out ranges of data from Cassandra or from HBase and run analytics on it externally, which is a valid choice once you pass a certain amount of data in your database. All right, so let's say we picked some kind of data model. Let's say later on I'm going to show a demo of an application which does some kind of analytics with tweets. So let's say we're going to be storing tweets. We're going to be reading a bunch of tweets off the Twitter fire hose, and we're going to store all of them. So what would be a good database, a good data model for just storing a bunch of tweets? Seriously asking. Not a rhetorical question at all. Row, thank you. It wasn't a trick question. Actually, I would have accepted any database at all, and then talked about why it's a good or not good choice. But yeah, row is good. Thank you. So a row would be a good choice, obviously, because each tweet is a fact. It's an immutable fact. A tweet happened. Chances are we're not going to mutate that tweet later because it doesn't change. It's not an object in a database which we'll need to update. So any kind of row database is going to be a very good choice because we can just dump all these tweets. Generally, row databases are excellent at just accepting huge amounts of writes. They have very high write throughput. So Cassandra or HBase would be an excellent choice. I also would have accepted document because a tweet can be expressed as a JSON document just fine. And you can do that. It's probably not as good of a choice. For example, even if I weren't, if we ignore for a second that I worked for Couchbase, I still wouldn't have picked Couchbase necessarily for storing tweets. I probably would have gone with Cassandra and HBase as well. But we'll later talk about a good use case where you would use a document database for that exact scenario. But all right, let's say we picked our data model and we picked our database. So now what? The next thing we need to talk about is the different trade-offs we have. And that brings us to the CAP theorem. And before I talk about it, how many people have actually heard of the CAP theorem? It's a very popular buzzword. Well, okay, judging by the amount of hands, relatively popular buzzword. It's very popular for people who read blogs about the CAP theorem. 100% of the people who read blogs about CAP theorem know about the CAP theorem. All right, so for those who don't, the CAP theorem is actually, the CAP conjecture is a conjecture that was offered by a computer scientist from Berkeley named Eric Brewer at the start of this century, which says that for any distributed system, only 2 out of the following 3 guarantees can be satisfied. It can be either consistent, available, or be partition tolerant. And each of those actually has a very strict mathematical definition. It's not just hand waving and saying consistent. Consistency in the CAP sense means that for any sequence of operations in the database, reads and writes, there exists an order that you can sort those operations where it appears as if every one of them is linear and happened instantaneously. In plain words is, if I write something to a database and you read that later, you should see what I wrote and not a previous value. So every value is consistent. So there shouldn't be a case where I write something for, let's say, a row. A second later, someone else reads that row and gets a value from before I had that. Okay, how would that happen? Obviously, if you can have a distributed system and write to any node in a distributed system, it would take time for the data to propagate. It's entirely possible for a system to be not consistent. It's actually, most databases that are distributed aren't actually consistent in this definition. Availability in this case means that for every request to a non-failed node, you get a response. Which, if you think about it, is a very, very strong guarantee because a response means a positive response. You get something back. You don't get a timeout. You don't get an exception. For every request ever to a non-failed node that didn't crash, obviously, you get a response. And lastly, partition tolerance means that the database or the distributed system can continue functioning despite the loss of any number of messages within the system. So obviously, this talks about network partitions. So if we have 2 nodes in our database and we have a network partition between the 2 nodes, they cannot talk to each other for a while. And a system which satisfies partition tolerance guarantees will continue working. So you can talk to any one of those nodes and eventually they'll synchronize between them. So if you think about it, let's just say, give an example of, let's say, a P system that guarantees that. Source control, right? GitHub. It's a perfect distributed system. It definitely satisfies availability because your own system isn't crashed and you can talk to it. You normally talk to your local system, so it's always available. It certainly satisfies partition tolerance because if you cannot do your push to GitHub now, you will do it later. And is it consistent? Obviously it isn't because it needs to synchronize for a while, right? So by definition, GitHub would be a sort of a P system. Certainly P, maybe A. And if you think the other way around, what kind of system would be, let's say, C and P, so consistent and partition tolerant, but not necessarily available. Let's look at databases. For example, most key value stores are that way. So key value stores generally partition your data into any chunks. So one key belongs to one machine. You can go to that machine and write the key. Someone else who reads it will read it from the same machine. They won't get a different value. But chances are, if there's a network partition and you try to read some of the keys, you won't get responses because they don't exist on a machine. And if the system has replication, so let's say like Couchbase, for example, which stores documents spread out throughout the system, and each one has a replica, a copy in a different machine. If the machine that has the main item is down, you can read the replica, But in this case, the replica certainly isn't going to be consistent. It could be old. The replica hasn't been updated for a while, for example. Right? So in these terms, the CAP theorem it's a very simplistic but very useful tool to think about distributed systems. Recently, it's been turned into a horrible marketing buzzword because, as with every cool concept, marketing gets their dirty hands on it and just turn it into a marketing thing. So if you go and read the documentation for any database, you will see them claiming to be AP or CP or whatever, and most of them aren't. It's very, very hard to be C or A or P in general because the CAP theorem, while it's a useful thought experiment and useful tool, it's a very platonic ideal of consistency and availability and partition tolerance, and no actual database satisfies all of them. So it's not a useful thing to claim about a database, but it is a nice thing to consider when you need to pick a system to store your data, because the one thing we obviously cannot give up when we are talking about a distributed system is partition tolerance. Because by definition, networks are not reliable. Network partitions do happen a lot. Anyone who's ever used Amazon or Azure knows that networks are definitely not reliable on cloud providers. And I've had nodes go down and disappear for weird reasons in pretty much every public cloud, and then suddenly reappear a minute later, and no one knows exactly why that happened. And even actual real physical hardware is not reliable. You know, switches fail, entire racks can go down, or the power supply can cut off. So if we assume that networks aren't reliable, there is no way we can give up partition tolerance, because you cannot build a system which is just CNP, just consistent and available. Because, yes, sure, it can work if the network is perfect, but as soon as a partition happens in a network, the system doesn't have a defined behavior. It just breaks down. It can stop working, it can explode, you don't know what's going to happen. So normally what we have to do is pick somewhere on the range between consistency and availability, and each one of those, when you talk about consistency, it's not one thing. It's not either you have consistency or you do not have consistency. It's a very wide range of just how consistent the system is and what you're willing to give up for that consistency. So normally when you pick a database, let's say we'll compare Couchbase and Cassandra, my favorite thing to do. That's what I do most of the time at work anyway. So we'll compare Couchbase and Cassandra, and by default, Couchbase leans towards consistency because it tries to read and write from the same node for the same key. So if I have a document named David and I write it to computer number 12, I will also always read it from there. So it's going to be consistent within a certain range, because it's not really fully consistent. If that database goes down, I'm going to start reading from the replica, which is definitely not consistent. But normally it trends towards consistency. Whereas Cassandra, by default, all the APIs and all the different default values in Cassandra trend much more towards availability and give up consistency. And they have what's called eventual consistency, which means if you wait long enough, the database will reach a consistent state. But obviously, since you don't stop doing everything and wait, it never actually reaches full consistency, but it does have much higher availability. In Cassandra, you can, for example, read from any nodes which have a replica by default. You can write to any node, and that node will pass the write on to the copies. And most databases also offer you tunable ways to lean one way or the other. For example, both in Couchbase, Mongo, and Cassandra, and pretty much every NoSQL database you pick, usually you have a programmatic API which lets you specify the consistency requirements for the read or the write. For example, in Cassandra, you can say, I want to read this object from any node that has it. I don't care if it's old or not old, just bring it to me. I want availability. It's important to get the item. Then you get the available item. Or you can say, I want to read all the copies of this item, or I want to read a quorum of the machines. So if I have 5 copies, I want to have the item that at least 3 of the 5 agree on, so the majority of the machines agree on, and if they don't agree on, I don't want the item, it's too old. So then you can force it more towards consistency, because then you read from more machines, and you trade off availability. If you don't have that many machines, you won't get an answer, but you will certainly get an answer that's more consistent or more correct for what you expect the data store to have. So it's a continuum where we want to trade on, and this is one of the major considerations when we're picking a data store, which isn't SQL Server, because you get what you get with SQL Server. So now we need to think about our business use case. Okay, so let's go back to the original example, which is storing tweets and doing some kind of, let's say, sentiment analysis on the tweets. Do we necessarily need consistency on the tweets? Do we care if we get a slightly older version of tweets, or if we store a tweet and it goes and it gets lost? Not so much. Mostly, we would, for example, in this notional system, we would actually prefer much more to lean towards availability to make sure we can keep working, and less towards consistency, because any kind of sentiment analysis or anything we can do with tweets is going to be statistics based anyway. We don't necessarily need to have all the data or the latest data. We just need to be able to get the data as let's say, efficiently and as reliably as possible. So in this case, we'll definitely look towards databases which are available rather than the ones who provide consistency by default. In a different case, let's say we're looking at a banking application, and instead of tweets, we're storing bank transactions. Right? Everyone's favorite example. As soon as we start talking about money, right? So classic example of a race condition: we're taking money from one account, we're writing money to a different account. Right? This is the kind of thing you really want to be consistent, because if you're reading the bank balance of someone in the middle of a transaction, and you read some old value, you might end up, for example, debiting something twice or going below zero. If you assume that your bank account cannot ever go below zero, if you try to read and update the value, and then someone else does that in a database that isn't guaranteeing consistency, you might deduct the money twice, or you might end up with a different value or lose a right, but it will actually be available. So if you want to trade off on availability, then maybe you won't be able to do the transaction at all, but if you do the transaction, it's definitely going to be correct. So as an example, everyone's used an ATM, right? The bank machine. So obviously, ATMs are a classic distributed system. You have somewhere a mainframe server with your bank balance, and you have a bunch of ATMs talking to it over an unreliable network. So of course, for an ATM system, we want partition tolerance, right? We wouldn't want to build one without. So we have the P. So what do you think? What do you think we would actually want, or what do you think banks decide to do? Do they pick C over A, or the other way around? How many people think that for ATMs, bank go for consistency? So if you withdraw, if you have $100 and you withdraw the $100, you cannot cross the street to a different ATM and withdraw it immediately and again, because you would be at below zero. How many people think that's the way it would actually normally work? About less than half. All right, how many people think they actually trend more towards availability? So if the phone line or whatever connects it doesn't work, it will still let you withdraw, even if you go below zero. Most people, and you are actually correct, because that's the way it works. Banks have absolutely no problem letting you go below zero. In fact, they enjoy that because they can charge you interest. So ATMs very much trend towards availability. Up to a certain amount. For example, if the ATM cannot connect back to the mainframe, it will let you withdraw up to a certain limit and no more than that. And eventually they sync up and you end up with a minus and have to trade your car in for whatever, or a kidney. Not that it ever happened to me. All right. So we've talked about the consistency versus availability spectrum. We've picked our database. Now what? Next, we get to everyone's favorite thing, which is performance, right? Performance is actually a very tricky beast. It's not something that people do very well at all. And the reason is because benchmarks are completely useless. Now, I know everyone has benchmarks, and all of them were written by their marketing department. I know Couchbase regularly puts out benchmarks, so I've seen them. And every database vendor puts out benchmarks, which shows them on top and everybody else on the bottom. So yes, all the benchmarks ever have been written by the marketing department or paid for by the marketing department. And the reason is, it's very hard to do a useful benchmark on a database system, especially when you're comparing cross families. So you can, for example, compare, let's say, Cassandra and HBase. There is certain logic to that because you would use them the same way. You'd have some different semantics, but you would use them the same way. And then you can do a benchmark, but then they have similar performance anyway. So that's not the basis for picking one over the other. But if you wanted to compare, let's say, MongoDB to Neo4j, how would you even do that, right? A write in MongoDB has nothing to do with a write in Neo4j. So, for example, right, let's switch over to my trusty terminal, and we're going to do a benchmark in live time of MySQL versus Couchbase. And for MySQL, luckily it comes with a tool which does load generators. It's called MySQL Slap. All it does is just run a bunch of queries. You can set your parameters, you run this, we can go into the database server and see that it is indeed doing some stuff. So if you zoom in here, we can see that it's doing quite a bit, about 2,000 inserts and writes per second, which is great, right? 2,000 is a lot. And if we go into the performance report, we'll see that each write takes less than 2 milliseconds, which is very little, and each read is 13 milliseconds. Awesome performance, it's great. And if we now do exactly the same thing with Couchbase, which, as it happens, also comes with a performance tool called CBC Pillow Fight. It's much more gentle. It's a pillow fight rather than a slap fight. And if we run this, suddenly we see 15,000 inserts per second. 15,000. It's 5 times as much as MySQL. Clearly, Couchbase wins, right? So, no, obviously not. So, did we learn anything useful from this benchmark? We learned one useful thing. Caching works. Because obviously, we're only hitting the cache for both databases. But other than the fact that caching works, which we assume the QA department checked as well, we didn't actually learn anything useful. And any other benchmark we care to try would actually be just an extension of the same idea. Right? The only way to compare performance of databases is if you actually model your use case to what you're actually going to do. Furthermore, an empty database behaves completely differently from a full database. So before you actually start doing a benchmark, you have to do a lot of work. To get useful results when comparing across different database families, you'd have to actually decide on your data model, build some kind of simulator twice, because you're comparing 2 databases, or 3 times how many you're going to compare, build something that decide on data model, decide on your consistency model, build a simulator which creates something that's close enough to what you're going to do anyway, run this and get some kind of result. And there's no way ever to approach real data. You can only hope to build something that shows you enough to be able to decide on what kind of performance you're going to get from your real future application. But most benchmarks really that ever get published are boiled down to just this slap fight versus pillow fight, completely useless numbers which don't actually tell you how the database is going to behave in your use case. Which is why picking on the basis of performance alone, as in the story I started with, has practically no value. It doesn't actually tell you anything about the database, and it's much more useful to talk about different properties of consistency and availability and different data modeling, and only then, once you narrow down the field of data from 100 databases to maybe 2 or 3, go and develop your data model to a late enough stage where you can actually do some kind of useful performance testing on one and the other and compare which one works for you. There's obviously a lot of repetition of labor. You'd have to basically do your work 2 or 3 times for the data modeling, but it's worth it because at this point it will actually tell you something useful about the real life. And more than that, you will need to do it with enough data to actually simulate something useful, because you don't want a year from now to discover that your database stopped working because 1 terabyte of data is very different from 1 gigabyte of data. All right. So now, before we move on, I want to do a very short demo because we have like 5 minutes left, I think, right? Yeah. Very short demo of this Twitter application that we were talking about. And we pretty much settled on Cassandra. So let's take a look at what we can do with Cassandra. Now, what I'm doing is I'm going to use Spark Streaming, which has an awesome plugin for Twitter. It can actually connect to the Twitter, to my Twitter app and stream tweets to me in real time. So Spark is very nifty for that. All it does is actually filter all the tweets by specific keywords. And I actually tried filtering for NDC, Oslo, and Norway, and I discovered that nobody tweets about NDC, Oslo, and Norway. So there weren't enough tweets to actually make a useful demo. So we're going to go with keywords that actually do generate a bunch of tweets. And we're going to run this and insert all of this stuff into Cassandra. And it takes about 20 lines of code to write a system which reads a stream of data from Twitter and writes it to Cassandra. It's actually very simple because most NoSQL databases have very good integration with big data tools. That's really where they shine and where they get used a lot, which is integrating with Hadoop and Spark and tools like that. So in this case, we have, with our Twitter utils, which come for free with Spark Streaming, we just create a stream of tweets. For each tweet, we pull out the text, username, and date, create a very large tuple from those, which is just a bunch of values, and simply store it save it to Cassandra. That's the Cassandra integration. It makes it very simple. I append that to my tweet stream, and this will run continuously and push all the tweets into Cassandra. So if I run this, it will actually hopefully work. And we can go to our Cassandra console and do something like select star from tweets. And select star from tweets, and there we go. Lots of tweets keep coming in all the time. We have 85 rows now, and so on. So, very good. And now that you have the tweets, what can we do with them in Cassandra? Not very much, as it turns out, because Cassandra doesn't really give you a lot of tools for doing stuff. For example, can we do something like sum of latitude, just for example, from tweets? Nope, because there is no function called sum in Cassandra. Why? Because it's very hard to implement aggregations over partitioned data stores, so you don't have aggregation functions like that in Cassandra. You have count, you don't have sum and average and all that. So in order to work with this data, we'll need to use integration with other tools like Hadoop or Spark or Solr to actually do useful stuff with the data, and we're just mostly using Cassandra to store it in bulk. We can do the same thing with Couchbase in the 3 minutes we have left. If we go over to exactly the same demo with Couchbase, we're going to upgrade it. We're going to bump it up a notch for something that will actually make sense to use for Couchbase. Now, you wouldn't normally do the same thing with Couchbase. It makes absolutely no sense, because even though it has all the same integration, it adds a lot of overhead to storing flat data. But when would we actually want to use Couchbase to store, or a database, document database for storing streaming data, is when we don't actually store the raw data itself. We can push the raw data somewhere else, like Hadoop or S3 on Amazon, and just store it there. And we'll use the stream of data to mutate some kind of state in our database. So for example, in this case, instead of saving raw tweets in Couchbase, what we can do is we can store a user document, which represents the user. And for every tweet, we can update the document with some new data. For example, the hashtags he uses. Or if we think about a real useful real-world example, where it actually gets used a lot, for example, in advertising. So we have a profile for every user, and we have 1 billion users. And every time a user clicks some kind of ad, we go and update the user profile to say that he likes these kinds of ads. So next time we come to serve more ads to the user, we can actually consult the profile, which constantly gets updated and mutated in real time, and show better ads. Or things like fraud detection, where we have fraud profiles for all the users, and for every streaming transaction in our fraud system, which needs to be very fast, we'll just interact with the database, update some kind of state of the user which is doing the transaction, make sure this is an actual transaction that is not fraud and the user isn't in Nigeria, and if so, it will let this transaction go through. So in this case, we can do exactly the same thing, and it looks exactly the same way. We'll use our Twitter utils to instead turn this into a JSON document instead of a tuple, and simply save it to Couchbase, because it has exactly the same kind of connector as Cassandra to Spark. And if we run this, we'll get all our tweets in Couchbase. And now, what if we want to do something better with them? What if we want to, for example, search tweets? We want to search or do some kind of real full text search, or we want to do some kind of analytics with it. Now, we could. Did it? Well, of course it did. And that's what happens when you try to do too much in your demos. And then if you run it again, I actually wanted to leave the Cassandra demo to run at the same time as the Couchbase. Not such luck. But all right, let's run it again. Now that actually will work. So now we want to do some kind of analysis on the tweets. We cannot really do that with Couchbase. Couchbase has some query tools, but they're not built for analytics. They're built for operational databases, which doesn't seem to be working either. Okay. And the best way to do this is to use the integration Couchbase has with Elasticsearch to push all this data into Elasticsearch and do our analysis there. So just like the way Cassandra works with Solr for its analytical part, Couchbase works with Elasticsearch. Now that we have stuff flowing into Couchbase, in the background it automatically can index stuff into Elasticsearch. And then we can do something like this. We can use the Elasticsearch plugin, which is called Kibana, to go and build a real-time dashboard on top of our Elasticsearch index and do things like count tweets per second and find the 5 top tags, or things like build a histogram of the most prolific users tweeting about stuff, show them on the map, and even do text search. For example, we'll find hello, no such thing. Let's go with USA. We have those, and any tweets that mention USA but do not mention Russia, for example, it keeps adding tweets, so there's a few of those. All right, so now we can actually chain tools together to get something much more useful than we could with just the database. All right, so I'm going to leave this up as a summary, and with that, I'm pretty much done. So we have exactly 1 minute for a question, and then we can all go have some ice cream. Any questions at all? Everybody wants ice cream, and nobody wants to delay everybody else. So, all right, well, thank you very much for coming and listening to me, and hope you enjoyed it.